state, only on the first site, and it's acting as the identity, so it's not doing anything on all the other sites. So this is very important for us to store it efficiently. The way we do it is you simply import netcat as nk. This is how we refer to netcat in general. It's a shorter way. Just import also numpy because it's always useful. Let's say I want to study a system made of a chain of, let's say, 5 sites with periodic boundary conditions. So the lattice is something like this, right? So they're interacting like this. This is site 0, 1, 2, 3, and 4. So let's say L equals 5. And now the way we write this Hamiltonian is we have this module in netcat called, first in netcat we have to write down the Hilbert space. So every piece in netcat needs to know on what Hilbert space it's acting on what Hilbert space we're working with. So we have this submodule in netcat called netcat.hilbert, which, I mean, it doesn't take a PhD to know that it contains various Hilbert spaces that you can use. There are several. In particular, the most important ones are the Fock space and the spin Hilbert space. I will be working with spins 1/2 in this case, and we have 5 of them. So now this is an Hilbert space object, okay? It tells you like the spin of the spins inside of it, the number, how many of those we have, and you can play with it, like you can concatenate 2 of them. So if you multiply 2 Hilbert space like that, you get a spin space on 10 sides. You could even multiply it by, I don't know, the Hilbert space of some photons, so a Fock space. So you will get the spins coupled to photons. You can do many things. Okay, so let's go back to the very simple Hilbert space, right, on 5 sides. The important things that you can do is that we want to get from it the states. Okay, so for example, you can get a random state in the Hilbert space, right? So this will be in the computational basis, and somehow it corresponds to a state that is up, down, down. You can ask the Hilbert space to give you all the states, which is just a very long list of all of them, like down, 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 up, etc., etc. Of course, this will only work if your state is sufficiently small. And then the most important things you have to know is that you can always ask him the size, so how many sides there are in the lattice, and the total number of states. So now we're working with a tiny system with only 32 states, but you could easily shoot it up to 20 or 40. Really, there is no problem. Okay, so now we want to write down the Hamiltonian, like this Hamiltonian here. So the most general way to do that is to go inside of netcat and go in the module operator, where there is everything you need to work with operators. There's a bunch of things. What we need to work with is the local operator. So it's somehow our sparse representation of operators, where we are not computing the tensor products of the identity, but we are just storing where each operator is acting on. So to create a like 0 operator, just create a local operator on this Hilbert space, right? So now this H object, you can, for example, I don't know, you can convert it to a dense matrix. You see that it's all 0. You could add 1 to it, for example. You see that you get a 1 on the diagonal. Like when you add it a number, it assumes that you're adding it to the diagonal. You can do a lot of things. So let's say we now want to write down our Hamiltonian, right? So let's assume that our parameters are h equal to 1.0 and j is equal to 1.0 also. So we can just do, I think there is a question. Yeah, I don't know how to.
Yes, please, I was about to say it. Artem, please.
So the question is a bit, I don't quite understand. So you define the local operator, but you haven't specified anything yet. So in principle, it could also not be local. So kind of what does it mean it's a local operator if you don't know what the entries are yet? Does it mean that it would be blocked if you try to set it as a full dense matrix or?
Okay, so you can always play with, let's say, full dense matrix. This is just, if you want, maybe it's a bad name. Local operator is just the way we use to represent operators in Netcat. What this command is doing is just creating an empty one. Like it contains many local blocks, and there are none here. Okay, so it's 0.
Like a zero matrix, basically.
Yeah, exactly. It's somehow a 0 matrix. The point is that in Netcat, like you can only work with local operators at the moment. So, I mean, you cannot really mix it with something that is not a local operator. So, I mean,
okay, I see.
But I mean, it can have a very, like it's local in space, but it can be very extended, the domain on which it acts. It can even be the whole Hilbert space. It's just that, I mean, then it will break down because it will be too computationally involved. So what you need to do is to write down this Hamiltonian, simply, I mean, treat it as somehow your matrices, okay? And we want to add the various terms. So the easiest way to do that is to just import from netcat.operator a mod, sorry, from netcat.operator import a small block of like a small submodule called spin. And inside of spin, you see we have all the various Pauli operators, so sigma x, y, z, plus and minus. So let's say we want to write down the this term, the local field term, sigma x, Hilbert I. So I is going on labeling all the sites. We multiply it by minus h, so it's our field constant. Like, it's the intensity of the amplitude of the field transverse field. So yep, for E in range, sorry. So now if we take our Hilbert space and we convert it to a dense matrix, you can see that, I mean, we're starting to have a few terms. Those are not diagonal terms, for example. So we have added in the transverse field. Now to add the coupling between the sides, I can simply iterate again for E in range L. Let's say I want to use periodic boundary conditions, as I said before. So I essentially want that when I is equal to 4, essentially, it must loop back to 0. The way you can do that is that imagine I is 4, right? You can simply add 1 to it, so it's 5, and you can take the remainder of a division by the number of sides, right? So this is just a trick to say if I is equal to 5, and just loop it back. So that's our J, and otherwise you can see that it's simply I plus 1. And now I can simply sum those terms, right? So plus equal J times spin dot sigma Z Hilbert on I times spin dot sigma Z Hilbert on J. And if I take this matrix, you can also convert it to a dense because it's relatively small, and you see that you have various terms. So you have all the terms on the diagonal now. Of course, you're not limited to the matrices that we implement in Netcat. You can, I mean, you can always create a local operator with whatever number you want. So imagine you want to create by hand the sigma, let's say the sigma Z matrix. So you would write the sigma Z matrix by yourself, right? 1, 0 on the first line and 0, 1, 0, minus 1 on the second line. And then you specify on which side you want it to act. So 0, for example. And this is, I mean, you can check out the documentation if you want. So like you can really write down any matrix and give it to those operators. So now that we have the Hamiltonian, of course, this is a super small system. So what we can do is we can use some exact tools that are inside Netcat in the namespace exact. And for example, we can use Lanczos to compute the ground state energy. It's minus 6.15. Of course, this is a tiny system again, so let's just keep it here for reference. Okay, so now, I mean, now the question is, okay, so can we use some variational model to study this system? So first of all, I will show you how to use models that are already inside Netcat, and then later I want to show you how to write your own models, which is the interesting thing to do. So inside of Netcat, unsurprisingly, there is a repository, let's say a module that contains a bunch of models that we have already written. You have a restricted Boltzmann machine with symmetries or without, just row ansatz, MPS. So I will pick now the just row ansatz, for example. And it's interesting to check what are the parameters that you can specify. So for example, you can see here that for just row, you can specify the data type. So I don't know if you're familiar with the just row ansatz, but essentially, the just row ansatz means that we are parameterizing our wave function as the exponential, in this case of sigma transpose, if you assume it's a vector, times a matrix W times sigma. Okay, so this is a scalar essentially, and then you take the exponential. So this W matrix, if you have n sides, then W will be an n by n matrix. Okay, and the data type essentially specifies what are the elements of this matrix. So they can be single precision floating point numbers, double precision, complex numbers. By default, you can see that they are double precision complex numbers. You can specify the function to initialize this kernel, this matrix. It means, I don't know, you want to initialize it all zeros or as a normal, like normally distributed or things like that. So what I want to do now is I want to specify the initializer. I want it to be, let's say, I want them to be normally distributed. So the initializer are hidden away inside of this netcat.neural network .initializers.normal. And you can specify the standard deviation to be 0.1, for example. Okay, so now we created the model and you can inspect it, and that's just telling you a bunch of those things. Now, this is just a description of the model. It's not itself. It doesn't have any parameters inside. We need to build a few more things. So the next thing we need to do is we need to build a sampler, right? That's because if the Hilbert space is huge, we do not want to compute the wave function, like we do not want to compute expectation values and other things on the whole Hilbert space. I'm sure Giuseppe already told you that like within this class of variational methods, when we when we want to compute the expectation value of an observable O over a state psi, what we actually do is that we write this as a sum of the various terms in the Hilbert space with a certain probability times a local estimator of those entries. But and then what we can do is actually rewrite this as a sum of a set of states sigma that are distributed according to this probability distribution, and we just sum the estimator for every one of those. So what we want to do is we want to sample this, and Netcat has many samplers inside of it, netcat.sampler module. In particular, I'm going to choose the Metropolis local sampler. And the only thing you need to do is to tell him that you want to sample like the Hilbert space we are working on. The other thing that you can specify is the number of chains. So essentially, I'm not sure if you're familiar with Metropolis Monte Carlo, but essentially the idea is that you start from a site, from a state, let's say sigma 0, which is let's say up, 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 down, for example, and then you have some procedure to generate the next state, sigma 1, which would be, I don't know, up, up, down, down, and so on and so forth. You generate the second, etc. Now, asymptotically, all those states will be distributed according to the probability distribution that you care about. Good. The point is that computers are more efficient when they repeat many times the same task. So what we do is that we don't do this for a single chain, but we do this calculation for many chains. So like my initial state, it's not just a sigma 0, but it's a sigma 0, a sigma 0 prime, a sigma 0 second, a sigma 0 third, and so on and so forth. And I evolve many chains in parallel, which do not talk to each other. Sigma 1 prime, sigma 1 second, etc., sigma 2 prime, etc. And so at every time step, I evolve a bunch of chains independently. But since I do this in blocks, the computer is actually faster at doing that. So usually we use 16 chains at the time, but depending on if you work with the GPU, you might want to increase it, or in some cases you might just want one chain. So that's what we have here. And then in Netcat, the central element, a very fundamental element, is you need to put the model together with the sampler into what we call a variational state, which means basically you have your model and you sample it with a sampler. And this together is an object that can compute the expectation values, that can give you many information, that has parameters, etc. So the way we call it a V state, a variational state. Again, this is inside netcat.variational namespace, and this you can create this as a MC state, Monte Carlo state. You have to pass in the sampler and the model. You can say you can also specify a lot of other things. You can always just ask, check the doc strings. For example, you can specify how many samples you want to take. You can specify seed. There are many things. I won't get into the details right now. But let's say we want, I don't know, 500 samples. So the first time you run this code, it will take a bit because it's compiling. And then we have this object, okay? It tells you what's Hilbert space, what's the sampler, how many samples it's taking, what's the state of a sampler, how many parameters we have, 25, right? Because this matrix is n by n. Now, the interesting things to do is to look, for example, at the parameters, okay? So Netcat uses under the hood JAX. I won't get into the details of it, but essentially JAX is a library made by Google for differentiable programming. Essentially, whatever you write using operations allowed by JAX can be differentiated, and so you can compute gradients of that code.
Filippo, can I interrupt you just for a
yes.
second? Could you
yes.
precise, perhaps I'm not sure it's that obvious, what n samples mean?
Yeah, so the number of samples means that if you ask to the variational state to give you a bunch of samples like this, right? It will give you an object like that has a certain shape. So here you see that the last dimension is 5 because every sample now it's one of those sigma states. So it's the configuration. It's a cat, so it has dimension 5. Then you have 16, that is the number of chains, right? Because I told you that we are doing this computation in blocks of 16 to be more efficient. And the last dimension is 32. And now if you multiply 32 by 16, you get 500, so which is 512, which is roughly 500. Essentially, this means that if you want 500 samples, we are doing enough steps in the Markov chain in order to get 500 samples. I don't know if that's clear enough.
Yeah, I think perhaps it's good to say that in the end you will do some variational calculation and you will try to optimize your state, and to evaluate your state and your gradient, as you will come in a few seconds. Yeah. You decide you take 500 samples.
Exactly. So it means that if you want, it means that the size of this set of sigma, the size of those sigma states that you see here, will be approximately 500. I mean, 500 yes. Rounded to the nearest integer that we can work with when we compute expectation values and gradients.
Thank you very much.
Yeah. So, So essentially, you see that now I was inspecting the parameters of this state. The parameters are always stored in this structure of nested containers. So this is a dictionary. The W matrix in this case is called kernel, so we can access it like that. And this is an array. You can check its shape, for example, the D type. It's going to be complex, these kind of things. So essentially, instead of a variational state, the parameters are stored as those as dictionaries or nested dictionaries. And what you care about are the leaf nodes. So all the arrays that are hidden away inside of those containers. And it might take a bit to work with it, but it's actually useful because it makes it easier for you to actually know what every one of those elements corresponds to. Parameters are not stored as a huge array. I mean, when we write formulas, we always say that it behaves kind of like a huge array, but inside of a computer, they're not stored as a huge array. Good. So imagine now that we want to, like, what you can ask to the variational state is, for example, to compute the expectation value of the Hamiltonian that we had before, right? This state.expect will give you an expectation value. And for example, in this case, we get minus 4.41. I mean, it's totally random because the parameters are random, right? It will also estimate an error and do a bunch of extra nice things. You can also compute the expectation value and gradient, right? So what this will give you is the expectation value again, and the gradient itself, which is again a structure of nested dictionaries with the same shape and structure of your parameters. Now, what you can also use the variation state to do is, for example, you can convert it to an array. So basically to the cat representation. This will take your ansatz, the just row ansatz here, exponentiate it, like compute it for every state in every cat in the Hilbert space and exponentiate it and normalize it. This is basically our cat. You cannot do this for big systems, but for small systems such as this one, it's fairly easy to do. So imagine now we want to, I mean, like we computed the expectation value before, and I mean, minus 4.41, it's very far from the ground state. So imagine we want to optimize to get towards the ground state, right? So what we can do is super simple. We can just, let's save the energy. Let's create a list. And what you can do is simplify the very simple list now to optimize this. So what you can do is for I in range, I don't know, let's do 100 steps of optimization. At the beginning of every step, you should reset the variational state, which means that you reset the sampler, because otherwise you will always get the same samples. So the samples are not, every time you, like, variational state computes the expectation, the samples once, and then it doesn't compute them again unless you ask it to. And you can see this, for example, I can show you. If I compute the expectation value of H, you see that it always gives you the same result, no? But if I now reset the state, which means reset the sampler, you get another result, which is more or less the same value, but not exactly. So in our training loop or optimization loop, what we need to do is reset the sampler at every iteration, and then we can compute the energy and the gradient, and we do the state.expect. I think state.expect and grad of the Hamiltonian. Now, you've seen that now we want to update our parameters, right? So you've seen that the state.parameters, the parameters are stored inside those nested dictionaries. And of course, you cannot sum dictionaries, right? Like if you do a dictionary plus another one, it makes no really sense. So what we want to do is actually we want to sum all the leaf elements of those dictionaries, or the arrays inside of those dictionaries. Okay, so what we can do is there is a function in JAX to do this. It's called jax.treemap. I can show you. I think I need to import JAX. Yep. So to give you an idea of what jax.treemap does, I can show you. Treemap essentially takes a function like this, lambda x equal dot, I don't know, x plus 1, and a dictionary. So imagine I give you a dictionary which has a, the first element is a, it's 1, the second element is 2, and now what this function does is that it returns you the same dictionary with the same structure, but the elements have been updated according to this function. Okay, and there is also treemultimap, which is a mapping function that acts on 2 dictionaries. Okay, and it wants a function that takes 2 inputs, x and y, and it returns whatever you want. In this case, I will sum them. And so you can see that in this case, I'm summing A, I get 11, and B 22, etc. So we want to do the same thing, right? So I want a treemultimap that takes an input, my parameters, my grad, my gradient, and returns me parameters minus, let's say, some training rate 0.01 times the gradient, and then I pass in the current parameters and the gradient itself. Those are the new parameters, and then I have to tell to the variational state that was that its parameters have been updated. I simply set the new parameters. And I will also log the energy to this very small list. Yep, let's see if it works. I will also import matplotlib, plot it.
So Filippo, stupid thing, we can't see the end of the last line of new of the tree multimap.
You cannot see it? Okay, sorry.
You see what I mean?
Like this, you see?
Okay, if students want to.
Okay.
I see. Okay, great, thanks.
I can do this. Okay, and now if I plot it, you should see that somehow, yeah, okay. Why is this error? Yes, this error is because actually when Netcat throws you like the energy, it's not actually a number, it's not, but it's actually a structure. You can see it like this. It's a stat structure that contains all the information, right? And you can access the mean, the error of the mean, but so NumPy doesn't know how to plot it. So when we log it, we actually need to, take the initial, the mean value. So what I will do now is instead I will rerun the optimization and I will reset the variation state to its initial configuration. Yep, and you see that we were starting from the initial energy minus 4.8, and we have a state that is, I mean, it should be closer to the ground state. X min equals 0, X max equals 300. Yeah, actually, in this case, it's super simple. So the just runs it is sufficient to get perfectly the ground state. Yeah, so that's it. So that's a very simple way to use a variation state in Netcat. Now, what I want to do is to show you how to improve this code a bit, and we can try to imagine that, I don't know, your professor asks you to compare, I don't know, the just row ansatz against the mean field ansatz, because he wants you to say how powerful is this ansatz compared to mean field. So let's also go to somehow a bigger system. I duplicated the notebook. So I will need to import, yeah, let's do this. So let's increase the size a bit. If we can even do 20 sites. Yeah, so before I created the Hamiltonian using these local operators. Actually, local operators are quite efficient, but there is an even more efficient way to write down the Hamiltonian, which is to know exactly what Hamiltonian we are going to write and hard code it. So since a lot of people work with the Ising model in Netcat, we actually have hard coded the Ising Hamiltonian. And to use it, the only thing you need to do is you need to define the graph on which you're working. Okay, so in Netcat, there is a submodule called netcat.graph, where you have many kinds of graphs like hypercube, square. Okay, these things is a bit a mess, but you have several. They are all in the documentation of Netcat if you go on the website. I want a chain with L sides again. Okay, and I will create an Ising operator. So Hilbert HI. You have to pass it the graph. You have to specify the field and coupling strength. To show you that those two representations are perfectly equivalent, I will temporarily put a lower number for L, because otherwise, I mean, they're too big to fit in memory. And what I will do is I will show you that, let's see, that the two, let's say that H2 dense and H2 dense are the same. Yeah, H is not defined because I forgot the hat. Yep. So yeah, you see this is all 0. I mean, we could even do notpy.all equal 0, and that's true. So they're identical. Okay, so now I will just delete the old code and just use this new representation because it's more efficient and faster. Yep. So we can also diagonalize this. Let's go back to 20 sides. We can also diagonalize this. It will take a bit. Yes. Will it finish? I think it should finish, but I'm not sure. Maybe I will crash my computer. I don't know. But okay, so yeah, now it worked. Okay, so now let's just try to rerun the same code. But I mean, we don't want to always write all this boring stuff about doing the optimization, right? So what we do in Netcat is that we have a bunch of optimizers. So you can just do the same thing again, and you can write down. We have another submodule, netcat.optimizer, with many optimizers inside. In particular, I'm going to take SGD, which is the same thing I was doing before, with a learning rate of 0.01. I will call it op, not a great name. And then instead of writing down this code by yourself, you can use the VMC driver, Variational Monte Carlo driver, which is an object that kind of does all these things and with bells and whistles and a bunch of other things for you. You simply need to pass him the Hamiltonian, the optimizer, and the variational state. Okay, and what he will do is that now you can, for example, and you see why it has bells and whistles, you can create a logger object, netcat.logging. I don't know, runtime log, which is just an object that stores like observables, expectation values, and a bunch of other things while you do the optimization. And you can do ground state.run. You specify, I don't know.
Please, can I interrupt you for a second, because I think
you're
going a bit fast. Can you explain what is SGD, for example, and what is Metropolis local? I think you didn't specify.
I said it before, no?
I think you didn't say what is Metropolis local doing.
Yeah, I didn't want to get in the details, but I can just.
What SGD? I mean, at least the acronym. Yeah.
Okay, so SGD is stochastic gradient descent. It means it's doing exactly this thing that I was doing here below. So it's taking the gradient, it's multiplying it by a learning rate, and it's using it to update my parameters. That's super clean. There are other more advanced optimizers like Adam and if you are interested, I urge you to go on the Netcat website, documentation, on the list of optimizers. You have a bunch here, and there is nothing written. Okay, we should improve those. Yeah, you have links to Wikipedia and a bunch of other things to see what they do. The momentum optimizers, and you have the formulas that they use. There are maybe holes in the documentation, but if you Google, for example, for the Adam optimizer, you will find what it does. I will use a very simple one, which is a stochastic gradient descent. Metropolis local instead, it would take a bit to explain what to do, but essentially it's an algorithm to, it's a sampler that essentially starts from a state sigma 0. Now I want to obtain this this chain of states sigma 0, sigma 1, sigma 2, etc. And what Metropolis local does is that it takes a sigma 0, like which is imagine up, 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 down. Then it at every iteration it will pick one state randomly. Let's say it picks this one, it flips it, so it gives me this state up, down, and then it computes a certain acceptance probability. So essentially, it computes the energy of this. Well, let's say it computes psi square of this and psi square of this. Okay, and then if the probability amplitude of this new state is higher than the previous one, it accepts it. It means that this state becomes sigma 1, and then you rinse and repeat this algorithm. Instead, if let's say prime. If sigma square of psi square of sigma prime is bigger than this is accepted. Instead, if it's lower, there is a certain probability which is exponentially suppressed to accept it or not, or reject it. So maybe it will accept it, maybe not. And this probability is given by the ratio between those two amplitudes. So the way you propose this move, so this acceptance rejection algorithm is common to all Metropolis algorithm. It's the Metropolis hastings sampling, but the way you propose a new move, so like for example here it picks at random one state and it flips it. It's typical of a local sampling. And you have many other ways, like you can propose moves based on the Hamiltonian, based on your knowledge of a system, based on the clusters in the system, based on what's like you can flip couples of sides. There are many ways to do it. You can, again, you can go on the documentation and look at the many samplers that exist and check their description, and there are many of them. Yeah.
So thanks. Actually, we have one question, but just before, since it's not the exponential, it's just the ratio of psi square, or no, or maybe I got confused. Maybe you're thinking about the log or something.
So
or am I wrong? Maybe I'm wrong.
No, the acceptance probability is in the space of a wave function, so it's an exponential. Okay, no, sorry.
I think the weight is just psi square, so I guess it's just the ratio of the weights.
Yeah, it's just, sorry, I'm saying it's exponential because
often we store the log.
Yeah, because actually our wave function, like our models, like this model, for example, is encoding, the Jastrow model here is encoding only the logarithm of a wave function.
Yes.
So for me, like the Jastrow here,
okay.
sigma is actually simply sigma transpose W sigma, and this is true for all models with Netcat. Like you are always encoding the logarithm of a wave function, and then we exponentiate it whenever we need it to increase numerical precision.
Yes, thank you.
But yes, you are indeed right that we are working like that. The ratio of the probabilities is just the ratio of the amplitudes.
We have another question by Juan Diego. I will just mention it. So there are optimizers in Netcat. Are they just wrappers from SciPy?
No, they are wrappers from Optax, I think. Yes, they are. I mean, they're not even wrappers. I mean, you could import Optax. This is also written in the documentation if you read it. So you can use optax.sg stopcast, I think. I mean, they have different name. Yeah, SGD. Learning rate. I think it's, let me check. Learning rate. Yeah, learning rate equals 0.1. And these, I think, will give you the same. Yeah, you see, it's exactly the same thing you will get out of netcat.optimizer.sgd. So if you want to, Optax is a very, very powerful gradient optimization library. You can write, you can use it to write very complex optimization algorithms, and it works with all the backend in JAX that is behind Netcat.
Okay, thank you.
So, okay, so now if we have all those parts, what I wanted to show you is that essentially, if you create this, what we call a driver, so it's just an object, the VMC driver, variational Monte Carlo driver, that somehow does this optimization loop for you. And what you can give it is you can also ask him to save the output at every step. We have a bunch of loggers, TensorBoard login, JSON logger, which just saves your data to JSON. So on a file, I'm gonna use the runtime logger, which doesn't save it to file, just keeps it in memory. So if you run this optimization, you should see we can, sorry, I need to import again .lib.pyplot. So plt.plot, I want to plot the energy again. And yeah, you see that in this case, I mean, I think I probably needed to do more optimization steps. So I'm gonna do it again. Yep, you see, like it got down to this value, and I might also plot the exact value, and like in this case, the Justro is very powerful. So there is a question, yeah?
Yeah, so the question is, so I noticed that kind of during these runs, the energy acquires quite a significant imaginary part. Why does it get it? Shouldn't it always be real? Or is it not guaranteed for a variational ansatz that it stays real?
Is it not real? I think.
Here, yes, but for instance, while we were running it, it had somewhere like
Okay.
0.001 or so, but it's still quite significant.
Yeah, the point is that the Justro ansatz that we are using is, if we inspect its data parameters, the parameters you can see are complex, right? So this means that the way we compute the formula we are using to compute the expectation value, this one, is not necessarily guaranteed to be real. I mean, we know that the expectation value is going to be real, so you can always take the real part by yourself, but we are not doing it for you because it might help you debug like issues that there are. So since you are summing many terms that should average out to, the imaginary part should average out to 0 if you sum all elements in the Hilbert space with the right probability, but this is not an exact calculation.
Okay,
so you get an approximately 0 imaginary part that you can throw away because you know that the expectation value is real. But I mean, we are not doing it for you. Okay. So yes, so you see that this is essentially this is how we use Netcat in practice. We use those drivers that allow us to do this, and also you could pass it like some additional observables to study during the optimization and other things. So now I would like to show you how to actually write yourself an ansatz. So I will start with a super simple ansatz, the mean field ansatz, okay? Because that's what I said before. So we need to import a bunch of things to do that, actually quite a few. So in Netcat, import netcat.nn. Netcat.nn contains a lot of tools from Flux. Flux is the library that we use. You can see it here. So Flux is the library we use to write neural networks from Google. You can use any library that works with JAX. So Flux, Haiku, JAX itself. But the key point is that, I mean, we tend to use Flux because it's the easiest one. Again, this is all written down in the documentation if you care about it, but to give you a very fast crash course to crash into it. The idea is that everything you need to write your models is inside netcat.nn. We will also need to import the JAX version of NumPy, and we call it JMP usually. I think this is all we need, but I'm not as JMP. So to write a mean field ansatz, for example, like essentially you need this to be a class that subclasses module. I mean, I would not get into the detail of why, just take it for granted. You can check on Flux documentation why. And essentially we need to write a method called call, which is what you use when you call a method, def. And this must be labeled decorated with compact. I mean, just take this for granted. Now, what this function must do is it must take in an input x, which is a batch of inputs. Basically, it's a block of states. It must compute the output. So for example, let's imagine that my input is, for example, let's see. We are working with batches of 16 states, so it's 16 states, right? Like this. So it's a 16 by 20 matrix. Now I want to write down the mean field ansatz. So mean field for me means that I want that the psi of sigma to be the product of some psi I on sigma I, where psi I on sigma I is basically psi I of up and psi I of down. So it's 2 numbers for every side. And as I told you before, like the ansatz you write must be in log space, right? So actually, this is the exponential of the sum of those psi I of psi I. And so our log wave function must encode this. The way I like now, this is not so trivial to do actually. So the set of parameters is what? It's for every state, for every side n, I have 2 numbers, right? Let's say that W is like, let's say for example, it's a random matrix or n times 2. Yeah, so n will be the last dimension of x, right? Because I told you before that X is this matrix where the first dimension is the batch dimension. So how many, like it's the group of states of cats that they want to evaluate, and n is the last dimension is the number of physical states in the system. So this is my matrix that holds all the variables. Now, how I can do, for example, what I can do is I can, like those states X you have seen before are all like either -1 or 1, down and up. So what I can do, I can first convert them to a logical true and false, so 1 and 0, and reshape it so that it has an additional dimension. Essentially now X is either false, false, true, true, false for up and down again, just that it's easier to work with. And it has a shape which is 1, 16, 20. So I added another dimension, and you will see right now. Now I want to double the size of this object. So I want to do concatenate the negation of X. So logical not and X itself along the first axis. So what this is doing now, X will have a shape which is 2, 16, 20. And basically the first block is true. So it's 1 where I have an up, and the 0 otherwise, and the second block will be the opposite. So it will be true where it's down and 0 otherwise. So now what I can do is I can use the in sum, which is just a smart way to multiply like different axes. Essentially I want to multiply X and W, okay, to get the output. So X has 3 dimensions, I, J, and K, okay? So the first dimension is the I should be summed with the first dimension of W, not the last dimension of W, I think. Yeah, actually it's easier if we do this like this. So I swap the dimensions of W. So I want to sum the first dimension of X, which is labels either if I want the up or down subspace, with the first dimension of W. And I want to sum the last dimension of X, which is the sides on every on inside my Hilbert space, inside of my cats. I want to sum them with the last dimension of W, so AK. And so the only 3 index is J, so the central one, which labels my batch dimension. If I do this and I didn't do anything wrong, yeah, I'm getting like this out, which is just shape exactly 16. So I got in like a 16 by 20 matrix. So a batch of 16 cats, and I get out 16 scalar numbers. Okay, so now I've written my algorithm. I want to put it inside of my model. So what I do is, yeah, I have all this stuff I've written before. I extract the size of my system. Actually, I think you need to do for now is you also must ensure that the input is always a 2-dimensional matrix. This is a limitation of Netcat at the moment, but hopefully it won't be there in the future. So we extract n as again. The only thing you need to do is that the matrix W, you need to write it like in the way that all this framework likes, not as you would like. So you have to call self.param, which is a function that creates a parameter, and you have to give it a name. Let's just call it W. you have to pass it the initializer. So netcat_n dot initializers dot normal with standard deviation 0.1. You have to give it the shape, which is true n, and the d type can, for example, do this. So d type, it's an object, and this, let's say that it's it's a real valued ansatz. Let's say we want this. Yes, there is a question.
Yeah, so it is more a bit about the theoretical part, but I'm not quite clear of what you mean by the logarithm of the wave function. I mean, it has to be a logarithm of a vector. Do you mean that it's a component-wise, an element?
Yeah, component-wise, yes. So essentially, like in your calculations, in general, you will need the psi of sigma, right?
Yes.
Inside of netcat, for like, if you work with those numbers, you have like very small numbers that are 0 and very big numbers. And floating point numbers do not like when you work with numbers on different scales. So what we do is, instead of parameterizing this object, we parameterize this object. That's all. So of course, when you want to reconstruct, I mean, the cat psi, which is the sum of all sigma of psi, right? Which means that it's sum of sigma, psi of sigma, cat psi. Then it simply means that instead of working with this object, we are working with the exponential of log psi of sigma cat psi. That's all.
Yeah, no, that's clear, and just a bit mysterious to me that you can kind of operate with this strange logarithm in the same way that you would do as for a matrix, like with these two equations that you've written, that it's a product state, and then if you take the logarithm, it's like an exponential of the sums. I mean,
but this is the property of logarithms, no?
It's true for matrices, but it seems a bit oblique that this is also kind of true if you just take an element-wise logarithm of a vector.
No, this is true in particular for element-wise operations.
Right.
Okay, so if this is clear. So I want just to show this. Essentially, now we have, like, we've created our W matrix, and then we are doing all the rest, and this is our ansatz, right? So now I can instantiate it. Yep, and I can just copy paste the same code as before. So I can take the variational state of this new model. I can take the optimizer again. I can create my VMC for optimizing the Hamiltonian, the optimizer, variational state, uguale state, equal the state, and yep. And then I write another logger object, and I run the optimization. I think I did 300 steps before, so I will do the same. I will save data to this new object. So now, yep, it works. And if I consider this plot, I try to plot also the new results. Mean field. Why isn't it showing the legend like this? Yep. So you see that, okay, I probably can increase the learning rate quite a bit, I guess. I'm not sure. Let's see. Yeah, so you see that it's not performing too bad, but I mean, of course, it's not at the same level. Okay, so now the last thing I would like to show you is imagine now we want to do the same thing with a restricted Boltzmann machine. A restricted Boltzmann machine essentially it means that your psi of sigma is the actually, let's work. It means that the logarithm of psi is the sum of phi of some how do you write it, of some nonlinear function g of the product of w of the rho of w times sigma plus a bias term. So this is what I mean by a restricted Boltzmann machine, somehow plus another term. So now this is already written inside of Netcat, but I would like to show you how to write it yourself. So let's try to write it ourselves again, right? So netcat.module. Let's see, we can, I can just copy paste all this code. Now, the way we call this block W sigma plus V, we call it usually a dense layer. Okay, so what you can do is you can just access it from here, dense layer. You can call it dense, and we can say that essentially you have to specify how many outputs, so how many eyes there are here, so how many features it has. In general, what we do is that we take the size of X and we multiply it by a constant. So for example, if N is as usual last dimension of X, at least should be, yep. So I do the same thing as before. If N is the number of sides, I want the features to be N times alpha, okay? And so I also store alpha as a variable, and by default it's 1. I think that's enough. Yeah, that's enough. And now, so what I need to do is simply to write down this function is simply take dense of X, which basically means, if you want, it means this. Okay. I want to pass it through a nonlinear activation function. So for example, log cosh. And then I want to return the sum of X along the last axis. So along this, of course, I don't want to sum along the batch axis, which is the first axis. I want to stress the fact that when I do those operations like sum, at least 2D, etc., I always use JNP, so jax.numpy and not numpy. This is because your model must be written to use jax and not standard numpy. But however, jax.numpy behaves the same as normal numpy, so usually you can just take your code and translate it to the new one in a very easy way. So the new model is simply this one. Let's say alpha equal to 1. And then I can once again copy all this stuff. How did it work? Copy, yes, does work. And paste, yep, great. So I create like once again the same model. I run the same optimization. Now I store results. Maybe let's just keep it the same. Log RPM. Let's run the same optimization again. Now maybe things won't work. Now things work. Great. Let's. Yep. So now you see. I mean, it would be interesting. Now you see that we got another optimization. It would be interesting to look at the end. Now is the epsilon beam, I think it is minus 24, minus 26. Does it work? Reversed, fine. If some, no. Yep. So you see that, wow, surprisingly, the just row is working better than the mean field, but I suspect it just because since the, if you want, This is because this RBM ansatz has more has 400 parameters compared to the just ansatz, which has 20 by 20. So I mean, no, still a lot. But I guess the problem here is that we need to increase a bit the number of samples that we are using, and it might behave better. Yeah, you can see that it's not at convergence. So what I should do is increase the number of iterations. And what we should see at the end is that it should be better.
The point you take is it perhaps a critical point? So
yeah, it's a bit
more difficult.
Yeah, it's an unfortunate point, but still I was expecting it to work. Yeah, we are around there. However, there is another trick that I think Giuseppe didn't talk to you about the other day, which is the stochastic reconfiguration. So I think that Giuseppe talked to you about doing the dynamics of the system, and I mean, I will just go very quickly about this. And essentially what he showed you is that if you have your state psi of W, means I think what he showed you is that if you have the state psi with parameters W at time t, you can define then phi of W at time t plus delta t as formally the action of U of delta t on psi of W. So this state, I mean, actually you cannot really compute it, but imagine we have it. And we can also define the state psi W plus delta W, right? Which is the state, the old state plus a small change in the parameters. And what Giuseppe, I believe, showed you is that you can write down an equation where you can essentially try to optimize the overlap between those two states. So you can write down something like psi of W, U of delta t, psi of W plus delta W, and you can try to determine the delta W that minimizes the above equation, this function above. And this allows you to compute the update at every step. And if you do this, essentially you obtain a formula that looks a bit like S times delta W equal to F, where, if you want like this, where S, it's a matrix, IJ, which is the OI star OJ. Essentially, this is the expectation value of the outer product of the OI and OJ, which are the log derivatives of your model. And Fi is your, it's the gradient of your model. So it's E log times O star I centered. So essentially what I'm trying to recall from you is that you can perform the time evolution of a system. I think here there was a minus I. What Giuseppe showed you is that you can perform the time evolution of a system by essentially computing at every step how to update the weights of your networks in such a way that you say that you try to compute, essentially try to say that the update to your parameters must actually maximize the overlap. I'm sorry, before I said minimizing, but it's actually maximizing. Essentially, you want to obtain the updates of your parameters at every time step in such a way to maximize the overlap between the state obtained by the unitary evolution and the new state you would have by updating your parameters. And this leads you to this equation, S times delta W equal to F. Okay, so now we can actually use this same technique to perform imaginary time evolution, so to optimize towards the ground state. So the way we do this essentially is, I will not do the calculation, but essentially we can replace the unitary operator here by the operator that would give you the imaginary time evolution. And what you will obtain is essentially a dynamical equation that looks again like before. So if I try to be explicit about dimension, it's this. But now S is it's the same object as before, or I star or J centered. And F instead is E lock O star I without the minus I. Essentially, and you can show that this Fi is exactly the gradient of the expectation value of the energy. Essentially, what I'm trying to tell you is that if you compute the gradient of the expectation value of the energy, which is what we are computing right now, and we solve this equation, so we instead of updating our weights at every step according to minus the gradient of F, we can update them according to S minus 1 F, because that's the solution of this equation. And this allows us, instead of doing a stochastic gradient descent, so a stochastic optimization of the energy, where we just go down with the energy, we try to minimize the energy iteratively, we are actually doing an imaginary time evolution, which means we are guaranteed somehow, at least if we were able to do exact sampling, we are guaranteed to fall down to the global minima and to the ground state, unless we get stuck on some excited states. So this is somehow, you can also see it as a second order optimization technique, so a more efficient optimization technique. And the way you do it in Netcat is, it's again very simple. I can go back to the old notebook. Okay, so I will just duplicate it. I will call it one intro as SR. This technique is called stochastic reconfiguration. So we just use the same notebook as before. Oh no, I'm using the wrong one. Sorry. And we just use the same notebook as before, but essentially what I want to do is inside of my training loop, I will use a new function. So this state dot quantum geometric tensor, which takes as input a structure that gives you all the details in how to compute this quantum geometric tensor. I mean, I really don't have the time to give you the details, but this S matrix, essentially, it's also known as the quantum geometric tensor of the model, and it somehow encodes the metric of the space of the wave function. Essentially, it tells you how, if you change by a tiny bit the parameters, how much far apart the two states in the Hilbert space would be, because the parameters live inside of the if you want somehow, sorry, if you want your parameters live in a space that is Euclidean. So if you take W and you take delta W, the distance between the two is simply the modulus of delta W. But now if you take the Hilbert space, psi of W is here, and psi of delta W, psi of W plus delta W might be very far, okay? And the quantum geometric tensor is somehow trying to represent this concept. So to use it, you need first to build this structure. You can find it inside of optimizers, and it has many elements, but I will just use the default values. And essentially, if you call this function, you get back an S matrix, which actually it's lazy representation of it, but it's not important. You just get it back, okay? And so what you can do, for example, is we want to use it to determine the updates. So we want to solve a linear problem S times X equal to F. So what we will do is this. It's very simple. At every iteration, we compute the gradient. We will compute the S matrix, and then we reshape the gradient in such a way to be that it's the solution of a linear system S given by S and F. So if you want, and we call it F. I want to find the X that solves S times X equal to F. And that's it. Everything else should hopefully still work. Yeah, of course it does not. Why does not it work? Doesn't it work?
A phi called grad and gradient, no? Or...
Spect and grad. No, this looks like it should work.
No, but next line you call. I know you call.
Yes, you're right. Sorry. It's because we get. Yeah.
No,
yeah.
You call the gradient, not grad. There's just an
in the next line, I guess.
No, but it's okay because it's gradient
it's
here,
here.
and
Okay,
that's
okay.
the lambda function.
Yes.
Yeah, I'm sorry, the screen is not large enough. No, the error was because I can show you. Essentially, if you compute the energy, we got the energy and the gradient F. We got the S matrix. Now, when you call S solve of F, what happens is that you get out two objects, like the new gradient, the delta W, if you want, this value here that solves a linear system, and an object that in this case is none, because one day it should give you back the number of iterations that it took, or like the error in the solution, but right now it's nothing. So yeah, so that's why you need to put this comma underscore. So if I run this optimization again and I plot it, you should see, like I can maybe show you the difference in using in doing the optimization with and without stochastic reconfiguration. So now I simply commented out this code and I simply use as a gradient F. And so I would like to show you that if I use those two solutions, okay. Surprisingly, it works better without stochastic reconfiguration. Okay.
It's a super small system, no?
Yeah, so going back to the big system of before, what we need to do is simply take the variational state again, build the stochastic reconfiguration and object, and use the optimizer with this learning rate, and you can simply provide the stochastic reconfiguration object to your variational Monte Carlo driver. So, I mean, basically what changes from before is simply that I'm adding this SR object to my driver. And now if I run this optimization, I will compare a run with SR to a run without SR to give you the idea of what happens. Of course, you can notice that without SR, the optimization is a bit faster. And if I take these on RPM, if I do this, yep, what you see now is that the restrictables machine is optimizing. It takes some time. You have this very fast optimization here, and then the gradient is very small. Instead, the stochastic reconfiguration one, it's the same exact model, it's just a different optimization technique, converges much faster. Like probably one thing that you could see is that if I plot the difference from the ground state, and I take the absolute value so that I can do a log plot, especially at the beginning, it should be not so good actually, but yeah. Okay. Still, you can see that it's converging much faster to the ground state, and we have a much better error on the ground state. So yeah, so this is a very powerful tool. Now, I have the last 5 minutes. I've shown you how to write your own optimization loop using the variational state, a bit how to play with the variational state. I showed you how to write your own ansatses, your own RBM, your own infield ansatz. The last thing I would like to show you is how to do the dynamics with Netcat, with the variational state. It will be super fast. So what I told you before is right. What Giuseppe told you a few days ago is that to do the dynamics, you have to essentially, like, what changes is that you have this minus I inside of the gradient here. Okay. So if you want, like, what we have to do now is simply pick a red color and add the minus I here. Nothing else. So if we take the code that we had before, let's try to work on a larger system, let's say 20 sites. I want to use, let's see, how can I do it? I can take, I want this, so it's faster. Okay, I will not compute this. For the model, I will be using the RBM that is provided inside of Netcat with a complexity type. Yeah, we want to use complex numbers. I would still use the usual Metropolis sampler. This is, I would use actually, let's say 1,000 states. Yep, so the first thing I want to do is to actually found the ground states. What I want to show you is essentially what I will try to do is this. I will determine the ground state of my system, okay, with optimization. And then I will do a quench. So I will add the strong field. So, and then I will do the time evolution, the psi in the t of h plus some, I don't know, some delta h of psi, okay, minus I. So what I do is I will start by running, by doing the optimization with the Hamiltonian. Netcat.optimizer.sgd learning rate equal to 0.0 0, 1, let's say, and variational state equal the state, and SR equal SR. Yeah. Okay, now we'll run this optimization for, say, 300 steps. Let's see if it works. Yeah. Import matplotlib as plt plot log energy. I just want to check that I reach the ground state. I'm sorry if I will take 5 extra minutes. There is no overtalk after me, right? Or there is?
No, it's fine. It's fine. You started later,
Okay.
so anyway, so that's fine. Don't worry.
Okay, so now I just want to find the initial state of my system, not to be a random state with random values in my wave function, but the physical state, like the ground state of this model I'm studying. You can see that by using complex numbers instead of real numbers, as I was doing before, it takes longer. Okay, so I somehow at the ground state. Let's see that this is good enough. So what I want to do now is, this was my training loop before, right? With my S matrix. So the only thing I need to do, I said, is to multiply by minus I the gradient. So that's what I'm gonna do. I'm gonna say that the F, my F vector, if you want, what I'm trying to do is this, no? So F is jax.tree map. So because this tree map acts on every set of parameters of, like, in every array inside of my parameters. And I want simply to multiply every one of those arrays by minus 1j, minus I. And I do this on F. And so what this code will do is it will be doing the variational time evolution of this system. Now, the important thing that I did not mention before is that when we solve this equation here, since we are inverting the S matrix, and I mean, let's see, I can show you if I take the quantum geometric tensor, it's this S object, okay? And if I convert it to a dense matrix, and I use NumPy, now this is an Hermitian matrix. If I use eigen, what is it, lineage? Yep. Now, if I plot those eigenvalues, you see that, I mean, many of them are very small, okay? So inverting this matrix is usually tough. So what we do usually is we add small numbers to the diagonal. Actually, it's 10 to the minus 2 here because we are adding something to the diagonal. Actually, when you create this SR object, you can specify a shift on the diagonal, like let's say 1 to the minus 10. And you can see that, yeah, if I put 1 to the minus 10, actually the smallest eigenvalue is 10 to the minus 5. So I think that's because the default is 10 to the minus 2. So you see that if I specify 10 to the minus 1, I'm just putting a cutoff on the smallest eigenvalue. And this helps stabilize a lot. But of course, the variation, so what I'm actually solving here is this equation. But that's not exactly the same equation, no? Like this epsilon, this cutoff that I'm putting. So we want to keep this cutoff small. Right now, I just put 10 to the minus 3. It's not the best value, but yeah, I mean, that's what we are gonna work with. And I will also try to monitor an observable, sigma x. I will build it now. So my sigma x observable will be the sum of spin dot sigma x acting on every side of the Hilbert space. Yep, I think. Blah, blah. Yes, so I'm taking the sum of sigma x acting on every side, maybe divided by L. Okay, so now what I will do is that at every step I will append I will compute the energy, because I mean I'm computing it anyway, and I will ask my variation state to compute the expectation value of sigma x, and I'm taking only the mean. And now, yeah, I don't have a progress bar, so this will take a tiny bit of time. And I have no idea of how long. It should be roughly 20 seconds, I think.
We have a question in the meantime.
Yeah.
So shifting by epsilon, the S matrix, does that make a systematic error, or is it what is
Okay,
something wrong?
So
I understand why you do it, but yeah.
Okay, so when you go for the ground state of the system, it doesn't give you a systematic error. It simply gives you a cutoff on the error on the energy that you can hope for. So if your epsilon is 10 to the minus 2, you cannot have a precision on the ground state energy that is above 10 to the minus 2. But then when you're there, you can decrease it slowly. So I mean, for example, if you know that your sampling error, the error because you are sampling, the wave function is of the order of 10 to the minus 2, you don't really care about it. On the contrary, when you're doing the time evolution, this epsilon, I mean, this epsilon can give you a systematic drift in your dynamics, and it does add up because you're adding it at every iteration, and so that it can be much more dramatic. So let's see. Yep. So what you see here is yeah, with this quench that I forgot to change the Hamiltonian. Yeah, I didn't change the Hamiltonian. So essentially what I'm evolving it's with nothing new. So what I actually want to do is I want to take the old Hamiltonian and add sigma x times, I don't know, 0.5, for example. So let's, I forgot to save the parameters. So let's run this again. So let's obtain again the variational state. This time I will save the ground state parameters. So what you see there are just the oscillations at the ground state. Yeah, so here I optimized, I'm saving the states, and now I'm gonna perform the time evolution according to a quenched Hamiltonian. And this is the last thing I will show you. I mean, you could, if you want, you can use Qtip or any other software to compute or SciPy to compute the exact time evolution. I don't have the time to do it now, but it's very simple. You just take the operators of Netcat and you convert them to dense matrices, and you do the calculations that you want to do. And yeah, and I mean, we see, you can see that you have oscillations. Those oscillations increase in size, and you start to have more error, more jittering because of the sampling, and the errors in your time evolution increase the time. And yeah, that's it.
Okay.
Sorry, I think, I mean, I will just redo this one last time because I forgot here. I was updating my parameters. No, 0.1. It means that my time step is 0.01.
Yeah,
so
that's what I was wondering. What
yeah.
is the x-axis? It's actually
it's time steps if you want. Here yes. I was taking, I should have had a plus instead of a minus, and 0.1. but I mean,
it's probably the same evolution.
Yeah, I'm just going backward in time. I'm sorry, doing this live. It's a bit.
No, that's fine. That's fine.
But
thank you very much for all this detailed tutorial. So we can take a few questions. Is there any?
Yes, please.
Go ahead. So unmute yourself, or perhaps let me say something else while people are thinking about question. Oh yeah, Artem, please go ahead.
I mean, I was wondering in general, I mean, it's a rather broad question, but kind of at the moment, for which applications are these sort of methods most competitive, or where would you advise to use them, let's say, as opposed to ED or some MPS or something like this?
I mean, ED, you will be blocked rather soon. I mean, with Netcat, now I was working with 20 spins, okay? So that means a Hilbert space of size 1 million. I can easily run 40 spins. I think if I turn on my GPU, I can run 100 spins. So you can scale up very easily. Very easily. Then, of course, there are many problems. The larger the Hilbert space, you need to be careful how you sample, especially if your system is, I don't know, frustrated, for example. But those are all issues you can work on one by one. Also, now I was working with very simple neural networks, but there are very advanced structures that also, for example, you can encode the symmetries inside of your systems. So you can reduce the number of parameters and increase their efficacy. What systems in particular this is best suited? I mean, I come from the field of dissipative systems. So in the field of, I don't know, was more closed system models like Ising and Heisenberg and the J1, J2 model. I'm not so familiar myself, but I know that I think the best accuracy on the ground state of the J1, J2 model has been done with RBM and over convolutional neural network ansatz. So I mean, you already have an answer.
Okay, thanks.
Yeah, perhaps I can say a few words.
Yeah.
Well, I think it's coming to be very competitive, if not, and it has a larger impulse, I would say, for indeed 2D frustrated magnets. In 1D, it's not perhaps not useful because the energy is already very strong.
MPS are very powerful in 1D. But
as a matter of fact, for some frustrated magnets like the J1, J2, I still think the energy is still like the 1D pass. The energy is still the best, but it will be changed, and perhaps going to 3D frustrated magnets, which essentially no method is doing correctly, is perhaps a way to go. Of course, I think perhaps Filippo, you can comment on that. For fermionic system, I think there's probably a lot to do with neural networks, and but it will also be in principle useful.
There are a bunch of, for fermions, there are a bunch of recent articles in the last year, approximately, by several groups, by Google and a bunch of others, that came out with structures, like neural network structures that encode the antisymmetric nature of the fermionic wave function out of the box. So whatever parameters you throw inside of your model, the wave function will be antisymmetric. And this is very powerful because then you can use, I mean, those D ansatz that represent them. I think it's kind of a future for chemistry computations, actually. They are still not perfect, those models, because they use a lot of parameters, but I think they're very, very promising.
Yes, I think so. Even though I guess for a bird-like model, it's not there yet, but
yeah,
maybe
so
it will come soon. We have another question by Jovan. Maybe you can unmute.
Okay, thank you. Can you hear me?
Yes.
So how about how would you actually compute entanglement entropy using your method?
So
is it possible?
okay, so you cannot directly access. Okay, so the question is always, I mean, imagine you have 100 spins and you always want, the Hilbert space is too big, so you always want to sample quantities with Monte Carlo sampling. So there are a few articles and there are a few methods to compute not directly entanglement entropy, which is linked to, if you want, von Neumann entropy, but some quantities that are related to it. So you cannot compute von Neumann entropy directly because it would require you to sum over the whole Hilbert space, but you can compute the Reni alpha 2 entropy, which gives you, I don't remember if, but it gives you a bound on the entropy of your state. So if you see, so from that you can also compute, I mean, entanglement Reni entropy by sampling. It's not the cleanest quantity to sample for a series of reasons, but you can do it. You can access it.
Yes, all integers larger than 2 Reni entropy are accessible once you have the state. You can sample the state.
Yeah, and, exactly. But in general, I think the most interesting one is the Reni 2, but I'm not, I don't know, maybe it's interesting also to compute the other ones, but I think the ones that give you the best bound on the von Neumann entropy is the Reni 2.
Okay, thank you.
Other questions?
So if there are no other questions, I would like to leave a few exercises to those of you that want to, that have a time and want to with the experiment with those states. I will connect myself tomorrow at, I don't know, the organizers can tell me when there is time in the schedule.
Let me see. Let me check the schedule. I think tomorrow students are, it's a long day because there's an evening session, but from 2 to 4 or eventually Friday afternoon is totally free. So perhaps you, Filippo, you can decide on which schedule fits you best and put that on Slack.
I think best is Friday, so I can, I don't know when it fits on Friday. But
Friday afternoon.
Yeah, let's say Friday at what time?
Whatever, it's totally free.
Okay, so maybe after lunch at 2:30 or something. I will connect again Friday afternoon around 2:30. So we can discuss.
You want to connect on Gather or through Zoom?
I don't know, as I can be on both. I don't know how you're organizing this.
We don't know yet.
Both. Maybe Gather, no?
Gather is perhaps better to have smaller groups. So, but okay, let's decide on the Slack.
Okay, it's just for informal discussions with those of you that
I think for that is better Gather, because then you all see each other and so on.
Okay.
And also because the Zoom is mine, and so I can take back my Zoom.
Okay, by the way, let me stop the recording.
Okay. But so let me just leave.
Yeah.
Maybe after the recording, I don't know. But let's see one.
Yeah, can you post? Can you post the notebooks on perhaps on Slack? Is that possible for you?
Yeah, I will do that after this is done.
And perhaps do you think you can leave your questions on Slack as well if you write them, but you can already explain them right now.
The exercises, you mean?
Yeah, you said you wanted to have some. Some.
Okay. So I can write them on Slack. That's good. So I mean, I will give 3 of them. I think one easier one intermediate, and one harder. That will surely not take you one day to do it. But so if in the future you are curious about this, you can just ping me anywhere and we can discuss about it. And I will be connected on Friday for it. So yeah.
Okay, let's do that. And we will please write that on the Slack. And thank you, everybody. Thank you very much, Filippo. And so for those of you who are sleeping, Filippo is available Friday afternoon at 2:30, probably on Gather. And
And I'll still connect now for 10 more minutes on Gather if you.
If you have an urgent question, please go to Gather, and Filippo and myself.
And I'd
will be
also like
around.
feedback about this tutorial. So if I was too fast, too slow, if you didn't understand
Yes.
anything, I'm very curious. So please let me know. Okay, and I don't bite.
Okay, thank you very much.
Thank
Let
you.
me start.
Bye bye.